In this first question, we will rotate the same region around different axes. So our region is bounded by the y equals root x graph, x equals to 9, and the x-axis. And if we want to sketch it, it would look like this. Then we need to find the endpoints so that later on we can take the integrals in that interval. Now the endpoints are 0 to 9 on the x-axis and 0 to 3 on the y-axis because our graph is y equals to root x. We should shade this region, and this is the region that we are going to rotate around different axes. So our first question is to rotate this around the x-axis. Since we are rotating it around the x-axis, we'll be dealing with the variable dx. So we'll use the endpoints 0 to 9. Now we need to sketch how the solid after revolution would look like. Now if you think about it, there is no holes in between, and the little disks are as drawn right now. Now we need to find the area of each disk and take that function's integral in the interval of 0 to 9. As you know, the area of a circle is pi r squared, so we need to define what r is. This is the interval of integral because we're dealing with the variable dx right now. And in this case, the r would be root x, since the r is equal to the y values and our function is y equals to root x. So we will put that in the equation as pi r squared, and we will take the integral of it from 0 to 9 to write the expression of the volume of the solid. The area is pi r squared, so we put root x instead of r, and we said pi in parentheses root x squared dx, which would be pi x dx in the integral of from 0 to 9. Our next question is to rotate the same region around y equals to -2. So we should sketch how the solid would look like. In all the questions, you should first sketch how the solid would look like. This time, again, we have the same region. Again, we're rotating around a line parallel to x-axis. So again, we're dealing with the variable dx. But this time, we have a hole inside the solid. So now we are still gonna use disk method, but we're first gonna find the big disks area like that one, and then we're gonna find the small disks area like this one. And in order to do that, we need to identify both their radius. So that is the radius of the small area, and that is the radius of the big area. So again, we're gonna do the same thing. The area is pi big R squared minus pi small r squared. So that is the area that we need to integrate from 0 to 9, because again we are in the same boundaries on the x-axis. So we write the p, and then we put a parenthesis, and then we write pi big R squared minus pi small r squared by identifying first what those r's are equal to. So the big R is equal to 2 plus the y values, and since the y values are equal to root x, we say root x plus 2. And then the small r is equal to 2 itself. So our equation becomes pi in parentheses root x plus 2 squared minus a 4 dx in the integral from 0 to 9. In the third part of the question, we need to rotate the same region around y equals to 3. So if we sketch how the solid would look like, we would get this. Now since y equals to 3 is the upper bound of the region, we would get something like this. Now if we look at the shaded region, we can see that there's again a hole in the solid. So again we have a pi big R squared minus pi small r squared situation. So we write the integral from 0 to 9, we write our pi, and then we put our parentheses, as always. So our big R is that, and it's between the y values 3 and 6. And since it's constant, R is equal to the 3 itself. So R squared would be 3 squared, which is equal to 9. And then if we want to look at the small r, now that is equal to 3 minus the y values. So since the y equals to root x, we should say 3 minus root x instead of the small r. Now if we put this into our equation, we would get a 3 squared minus, in parentheses, 3 minus root x squared. And then we put our variable dx in the end, and this is the integral that we use to find the volume of that solid. In the fourth part of this question, we are going to rotate the same region around y-axis. Now that we are rotating it around the y-axis, we will be dealing with the variable dy instead of dx. So this is the region that we will rotate, and this is how the solid would look like once we rotate it. So we're gonna rotate it around the y-axis, and there is again a hole in the solid. But this time our interval of convergence is different, since we're dealing with dy instead of dx. Our interval of convergence is between 0 and 3, because those are what the y values are in between. The x values were in between 0 to 9, but since our graph is y equals to root x, now it's from 0 to root 9, which is equal to 3. So now we're gonna find the big R again, like in the previous one, but we're gonna write it in terms of y. Now that is our big R, and it's constant, and it's equal to 9. So we're gonna again write our equation as first pi, and then we're gonna put our parentheses, and then we're gonna write the big R squared, which is 9 squared, which is also equal to 81. Now to find the small r, we need to look at the y values. And those are 9 minus y squared. Why y squared? Because since our equation was y equal to root x, our x is equal to y squared. And since those are equal to x values, we should write y squared instead of the small r, and this becomes our final equation to find the volume of the solid. Again, if you look at our small r, those are all equal to the x values. And our x values is equal to y squared because of what we were given in the beginning of the question. In the fifth part of the question, we will be rotating the same region around x equals to -1. Again, since this is a line parallel to y-axis, we will be dealing with the variable dy. So we're going to write our integral in terms of y values. This is our region. First we need to sketch the region, and then we need to sketch how the solid would look like if we turned it around x equals to -1. This is x equals to -1 line, and if we were to rotate it around this line, we would again have a hole in between. It's similar to the previous one, because again we'll just need to add some numbers to our previous big R and our small r. This time our big R is, instead of 9, since we have a +1, it will be 10. Our small r, instead of y squared, it will be y squared plus 1. And then the rest of the question is again the same. So pi big R squared, our big R is 9 plus 1, which is 10. And then our small r, again in order to find the area of that small circle, is y squared plus 1. So we need to write the integral from, don't forget, 0 to 3, because now we are dealing with dy's and y's. So our boundaries are 0 and 3. So from 0 to 3, we need to put the pi, we need to put the parentheses, and then the rest is just writing big R squared minus small r squared and dy in the end. Now this is our final equation in order to find the volume of the solid. In the last part of this question, we will rotate the same region around x equals to 9. This is an easier one because this time we won't have any holes in between. Again, we will be dealing with y's and dy's. Again, our boundaries are 0 to 3, but this time we don't have any holes. Because if we sketch how it would look like when we rotate it around x equals to 9, we can see that our region will look like this. That our solid will look like this when we rotate the same region. So all we need to find is 1r, which is equal to the 9 minus the x values, which is equal to y squared. So our r is equal to 9 minus 9 minus y squared, and that is all we need to find the area pi r squared. And then once we take the integral from 0 to 3, then we will be done.